Hello everyone, welcome once again to the TPS colloquia. Today we have the pleasure to have Nikhil Sarin telling us everything about Redback. Nikhil is a postdoc at the Oscar Klein Center. Nikhil, please take it away.
Awesome. I hope everyone can hear me clearly. Thank you, Priscilla, for the invitation. It's my pleasure to talk about Redback, which is a software package for modeling and inference of electromagnetic transients that I, alongside many other people, have been developing for over 5 years now. So I don't really need to motivate the need for, a modeling and transient inference package in this audience, but just in case there is some people here that don't really believe in the value of understanding how transients are valuable in terms of their inference, the plot I want to really highlight is, the first one in particular at first, which is just showing the rate of transients detections per year. And so it's been growing pretty rapidly, but then, we're about to really get into the era of LSST and, other large scale surveys soon afterwards. And so the number of transient detections and high quality transient detections is going to increase quite dramatically. And, it's all well and good to just be able to classify these transients and say, all right, we had 100,000 1As or 10,000 TDEs, but at least as astrophysicists, we want to work out what are the properties of these 1As and what are the properties of these TDEs and so on and so forth. So really, that's what the software package is all about. And so, it's about, if you look at the plot at the bottom, this plot from Villareal 2017, where we can take an observation, such as the observations of the kilonova, the very first kilonova we observed in detail from a binary neutron star merger, and we can fit it with physical models to try and understand how much gold was made and platinum and various other things and so on and so forth. So this goes in two ways. We want to understand what transients look like, but physically. So, if you change the ejecta mass of a supernova, what does that do to its light curve or its spectrum? But also empirically as well, so if we want to model some kind of luminosity function and draw a volumetric rate, we might not necessarily care about the physical parameterization of the model, but something that can capture all of these different diversities. At the same time, and particularly pertinent to this audience, we are interested in working out, all right, what does a transient actually look like in a particular survey? And how many transients should we expect to see? Or what can we actually observe, infer from observations? What is the precision of our measurements if we actually have an observation from a particular survey? So with that in mind, that was sort of the motivation to design this package. And it started off getting developed in 2019 and became a sort of a long-standing project. And the whole motivation was to also make this thing a modular, open source pip installable package such that, everybody could use it. And it's something that is adaptable to expert workflows. So, this is detailed things like how you treat the data, what are you assuming about your noise and the type of data. So if you're looking at just magnitudes, or you're interested in looking at the spectrum, or if you're looking at X-ray data, you might be interested in photon counts itself. So at the same time, it should be adaptable to this sort of really intense workflow, but something that a novice user who's just beginning into the field can come in and fit their favorite transient with a few lines of code. Another motivation was to also have something that was providing a unified interface for physical empirical models. So one of the things that is quite problematic in transient inference and transient modeling is that there's a whole bunch of different places where you can find a model for what your transient is supposed to look like, what a GRB is supposed to look like, or what a kilonova is supposed to look like, or a supernova, etc. But there's no one unified interface that provides a large library of models that you can just, you only have to learn how to use one tool to be able to understand all these different transients look like. At the same time, there was a desire to make this thing end to end. So you should be able to go all the way from real or simulated data and investigate or develop new models and do inference, i.e. fit the observations all in one workflow. And as well, because it's becoming increasingly common that we'll have joint observations of, for example, we often have a spectrum and photometry together, or a GRB afterglow that is contaminated by a supernova or kilonova, or in the rare instance, we have gravitational wave data alongside a electromagnetic counterpart. We want to be able to analyze these things together. So the framework of the software needs to be flexible enough to handle that. So with that in mind, this is sort of the overview of what the Redback package overall looks like. Essentially, it's a package made of different sort of sub-packages. And the idea is that at any point you are not, happy with, or you think you can do a particular aspect of the job better, something in Redback should basically the entire Redback workflow should be able to adapt to some user just swapping in a different part out. So in particular, what I mean about this is, for example, if you believe you have better models than what is available in Redback, you should be able to just simply plug your model in without ever having to touch the backend. And I'll show how that works in just a sec. At the same time, if you believe that you have, a better way to do fitting, such as, Bayesian inference, and you've got this new state-of-the-art sampler that is not implemented in Redback, you want to just plug that in. And again, that is something that we provide an interface for, as well as things like, you could plug in your own data that you're getting. So there's interfaces to get data from various different sources. But again, if you have your own data, you can just plug that in. Similarly, you can simulate things in serious detail and so on and so forth. So all of these different modules come together for different workflows. And overall, what Redback is, it's basically a collection of sub-modules that are all coming together to do transient modeling and inference. So the primary sort of three workflows that, Redback is, predominantly used for in the field at the moment is sort of, what's highlighted by this work pathway, which is where you would have some data of a particular transient that you wanted. You would load this up into what we call the transient object, and I'll show that in just a second, which is essentially where all the processing and all the cohesion happens within Redback, as well as some additional functionality that I'll show as well. And then you would specify a model that is ideally implemented in Redback already, or you plug your own in. You set a prior. So a prior is essentially just a distribution of what your parameters are in your model. So it's just a belief of what you believe each parameter is distributed as. You would then again set out a likelihood, specify a sampler, and you would fit. So now an expert user, wouldn't have to deal with a lot of the minutia that is involved in this. So for example, sorry, when I say I meant the novice user wouldn't have to deal with the minutia. So for example, the sampler would be chosen by default. The prior would be chosen by default. The likelihood would be chosen for default. So a novice user could go all the way from, getting the data to fitting an object and getting a result in about 6 lines of code. But at any point, if they are an expert and want to modify things, they can go in ever more detail. The other workflow we predominantly see is, people are just interested in simulating observations and then fitting. And they're essentially the modules all linked together where you would choose a model or provide your own. You would simulate observations through the simulation module, and then it's basically all the same. You would create a transient object and you would fit again. Or at the same time, you can, instead of doing, one single object, you can simulate a full survey. And so, for example, this is quite commonly used for ZTF and Rubin simulations at the moment, where you would essentially just simulate what a year of a particular type of transient would look like given a choice of model. So digging deeper into the different modules. So for example, if you're interested in just using Redback to get data, and again, this is something that provides a cohesive interface for getting and processing the data. So you don't have to worry about how exactly to find the different, what the API calls are, etc. So for example, there's a lot of people that have given talks on brokers here. So if you wanted to download data from Fink, you would just specify the name of the transient you were interested in. You would say Redback get data, get Fink data, and you would specify what type of transient it is, which is hopefully something that it's classified on. And then all basically with just 2 lines of code, you've got all the data for the photometry of this particular supernova. And then below, there's something for LSST, which is another broker that is going to ingest LSST data. Similarly, so the open access catalog, which was this wonderful resource where data was available for, across a whole bunch of different wavelengths for different transients. So the API for that is still alive in a way through this Redback interface. So for example, if you wanted the TDE data for PS18KH, which is a particular TDE people might be interested in, again, the same interface works and you can download the data. If you're interested in GRBs, if you want the time tagged data, so the exact photon counts, arrival times from BATC or Swift, you can do the same thing, or you can get the XRT data from Swift and so on and so forth. So Redback with 2 lines of code gets that data, processes it, so it's all very cohesive for you. And this data is saved as a text file returned in Python as a data frame. And so, you can mess around with it, do whatever you want. And this is pretty quick as well. So if you just want to ingest lots of data at once, this is a nice resource to do that. So then what actually happens with Redback is that one would download this data, or say they had their own, they would ingest this into what we call the transient object, which is sort of where the magic in Redback sort of really happens in terms of this is the module that sort of links everything together and basically communicates with all the other modules as well as doing some other processing. So say, for example, you had the data for this particular supernova on the top line on the right. Don't ask me to say its name. ZTF names are ridiculous. And you wanted to look at the flux data for this transient. You would just load up the supernova object for this transient, of a supernova transient object. And now all of a sudden you have this transient object, which can do a whole bunch of things. So essentially in Redback, there's about 6 specific classes for specific transients like supernova, tidal disruption events, GRBs, long GRBs, kilonovae, and and then 2 generic classes, which are essentially for a time domain X-ray or gamma ray transient or optical transient. So that's the 2 generic classes that are essentially for scenarios where you don't know what type of transient it is, whereas the child classes enable some extra functionality and aesthetics of plots, etc., based on the fact that that this is definitely a supernova. And so that enables extra sort of functionality as well. So for example, if you had private data and it was stored in a text file, you would just simply load up the transient object for in this particular case, I'm loading up can people see my cursor? I'm guessing not. Yeah, so I'm guessing not. So I'm just going to say in the bottom.
No, sorry, we don't see your cursor. We don't.
Thanks, Priscilla. So you in the bottom snippet of code, I'm showing that you can load up a data, which is just a pandas data frame. It's got a bunch of attributes. And this particular case, I'm interested in the flux density data for an afterglow rather than the flux, which was the top example. And then I would just load up this data and create an afterglow object. And now I can do a whole bunch of things, and I'll show that. So immediately, once you have the data loaded up, one of the things you can do is, plot it. And this is something that, it's an aesthetic thing, of course, as well. So, you might not like the look of the plots, for example, but these are all things that are just matplotlib. So the point is that you have the transient loaded up, you have it all processed with, 1 line of code, and you can even download it with 1 line of code. And then, you can just plot it, and things like, the axes labels or the colors, etc., are just keyword arguments the same way they are keyword arguments for matplotlib. And so the axes are returned, the figures are returned, and you can play around with what the data looks like. So in left-hand side, there's a transient.plot data, which generates a plot like this on the left-hand side, which is just showing all the in this particular case, the labels were auto-generated because I had loaded up flux density data for an optical transient. And so this is just showing what that looks like. Similarly, there's a plot multiband, which is just going to put everything on one panel, etc. But that's all well and good. That's just doing simple things like plotting. There's additional functionality, such as, for example, if you wanted to fit a Gaussian process to the data. So on the left-hand side, I have a real transient supernova some superluminous supernova. And I wanted to fit a Gaussian process to that data just to be able to interpolate and get quantities as a function of time. So with basically one line of code after I've loaded up the transient, I can fit any choice of kernel I want or let it be a default choice. I can even do things like fit a mean model on top of a Gaussian process and various things like that. On the right-hand side, I'm showing you essentially the same thing, but there I'm actually fitting a blackbody to the data and then estimating the temperature and flux and radius of the data, and then showing what the Gaussian process. Essentially, with a few lines of code, you can go all the way from downloading the data to fitting a GP or, for example, temperature and radius evolution. And you don't have to do anything for that. It's all sort of just inbuilt. But again, things like, for example, if you don't like the default choice of the kernel or you think that there's a better mean model, these things are just easily adaptable. You simply pass them in. So the actual bulk of the package is what is in the models themselves. So in Redback, there's about 150 models that are implemented, and these range from sort of phenomenological models to surrogates of numerical simulations. So when I say phenomenological, I mean something like, for example, the SALT model, which doesn't have any physics in it, it's just an empirical model. Whereas when I say surrogates of numerical simulations, I'm talking about these are collections of numerical simulations, radiative transfer or radiative hydro, that people have done, and then we're building a machine learning interpolator so that we can interpolate between the grid, numerical simulations in the grid. At the same time, there's also unified interfaces to many other modeling packages. So, for example, all models in SN Cosmo, AftergloPy, or MOSFET, etc., are all just implemented in Redback and are callable directly. And so when I say that they're callable directly, the layout looks something like on the right-hand side, which is just showing you that it's essentially just a function that you call. So I've specified the function as RNet bolometric. So it's the bolometric version of the RNet model for supernovae. And I specify a time array. It's just an arbitrary time array. And I specify some values for the parameters of the model. And again, this is all stuff that is incredibly well documented, as I'll show in a little bit more detail later. And there you have the bolometric luminosity on the time array that you actually wanted. And so you have a continuous representation of the bolometric luminosity. You can just simply change any of the parameters, and that will change the physics of the model, essentially. Well, it'll change at least the parameter of the model. The physics is also changeable. So, for example, if you wanted to change the way the diffusion of the bolometric luminosity is controlled, you can simply pass in a keyword, and that'll change that within controlled outputs, for example. So there's a whole bunch of different models, and the key thing with Redback is that all of these models are things that can output in multiple formats. So for example, if you're interested in flux density, assuming it's at an effective wavelength, you can do that. Bandpass magnitude for any filter, you can do that. Flux, again, similar thing, a bolometric luminosity, or just spectra as well. And this is true for basically every model, apart from some that are specifically for spectra or things like that. So for every model, we implement a default prior. And as I was saying earlier, when you do Bayesian inference or any kind of fitting, you ideally need a prior, which is setting some sort of bounds on various parameters, some expectations on what the shape of each parameter is. So for all models, we implement a default prior, which is basically just some simplistic form of what we believe each parameter behaves as. So for example, I'm showing you the default prior on the top of the RNet model, which is, pretty simple. It's just saying that, for example, the ejecta mass is uniform from a very small value to 100 solar masses, or the opacity is from 0.05 to 2. At any point, if you wanted to change the prior, you would basically just specify the prior you wanted. And basically almost any shape that is reasonable, analytical, is pretty much just callable as a string, essentially. So for example, if you want it to be Gaussian, you would just say Gaussian prior instead of log uniform prior, and so on and so forth. You can also set obviously a Dirac delta prior, which is, or just a float, which is just saying that this value is always the same for whatever reason. But you would do this for things like, for example, redshift, if you have a good spectroscopic redshift. The other thing you can do is you can sample from this prior with very complicated constraints. So you can put complex constraints on the prior to try and mimic what you might believe is, your selection or something else about your transient. So one of the ways we deal with numerical surrogates, which are only valid for certain regimes, is we would put a complex constraint on the prior such that it never draws a random sample that violates that constraint. So as an example, I've just written up a little function there, which is saying that any supernova that you draw from an arbitrary prior is not dimmer than 24th mag at peak, and that the peak is less than 150 days. So it's just a completely made up thing, but it's just an example of what you can do. And in particular, it's an SDSS R band. And so all of a sudden you would write down this constraint prior, and there's plenty of constraints that are written in Redback, so you can see how it kind of works. And once you sample on it, which is shown in this last line over there, population samples equals priors del sample, and in particular 50 random samples, all of the samples that will be drawn from this constraint prior will not violate this constraint. And so you can see that this is one way to handle very complex priors that are not really easily written down as bespoke. Each parameter has a specific shape. So when you have prior set up or you have your model written down, one of the things you will really be interested in doing, for example, in this audience in particular, is simulating what different transients look like. So within Redback, as I talked about earlier with the simulation module, there's essentially very simplified interfaces to simulate what any transient it looks like in ZTF or in Rubin. And so both of these surveys are essentially just implemented as is currently. So the correct, well, at least what I thought was the up-to-date OPSIM summary, table that keeps changing. But the whole point is that you can also change that as the survey gets updated. Within a few lines of code, you could go essentially simulate the full 10 years of Rubin. I have personally never done that. 10 years is too much for me, so I only look at 1 year data. So on the right-hand side, I'm showing on the top panel, basically within a few lines of code, you can simulate what a kilonova would look like in ZTF. And then the bottom, I'm showing what a supernova would look like in LSST with particular some cadence table that I had from OPSIM summary. And so any Redback model or any user provided module can be used with the simulation module to essentially do the same thing. And so at the moment, as I said, only ZTF and LSST Rubin are correctly implemented with the official tables. But at the same time, if you have a more recent table of pointings, essentially what the telescope's doing with its limiting magnitudes, etc., you can just input that in, or you can make it up. So for example, if you wanted to sort of make up your own survey and see what the transient would look like in that particular survey, you essentially would be able to just generate this table of pointings. And so there's utility functions in Redback to do that. And once you have that, you would put that pointings table into this sort of simulation module and be able to just essentially generate what the transient in particular would look like, any particular transient. So on the right-hand side of the parameters of the transient in particular I was interested in. So we actually recently used this in Meet, actually, I think did this, right? Where we recently did this for the Rubin TOO paper. So we used the Redback simulation module to essentially capture that. So once you can do that, there's, a whole heap of things that enables is, for example, once you have the simulated data set, you can do studies like validating, whether when you have your observations, whether you can actually fit them properly and whether your whole workflow works and what constraints that you can actually expect from your observations as well. So this is one of the sort of powerful ways you can go with machine learning and Bayesian inference, etc., and just fit your observations and see what you constrain about your various parameters. And the whole point is that the interface, once you have the simulation done and the transient object loaded up, it's identical as if you were working with real data all along, because of the modularity and because of the way the whole workflow is set up. And so on the right-hand side, there's a few plots showing how we've done this. So the top plot is from the TOO paper led by Igor, showing essentially what a simulated TOO kilonova would look like potentially. On the bottom left is an example of what gravitational wave and electromagnetic data jointly analyzed would give you, and on the right-hand side is what you can infer about the kilonova in particular with different models, etc. And all of these plotting, etc., are Redback as it is, with the very minor aesthetical changes that are just plot to matplotlib. So these things are just a few lines of code to generate. So as I was mentioning, a novice user, the whole idea behind Redback is that a novice user should be able to go from all the way from getting data to fitting something in a few lines of code. So here is essentially what a novice user's workflow would look like. They would get data on the right-hand side, as the snippet shows. For Laser, for example, they would create a supernova object. They would load up the default prior for the SALT2 model. They would set the redshift. So in this particular case, this redshift is spectroscopic, so you don't need to worry about errors or anything, at least not really. And you would fit it. And so within 7 lines of code, you have a fitted result. And so this is full posteriors on all the SALT parameters. And this is, going to take a few minutes to do. But at any point, for example, if you believe that you had a better understanding of the likelihood, you would write the likelihood, and I'll show that in just a second. You would basically expose what the likelihood looks like and pass that in. And so then instead of using a by default Gaussian likelihood, you might be able to put something with covariances in and various other things. Or for example, if you didn't want to fit SALT2 and you wanted to fit a different model, you would just change model equals SALT2 to basically some other model as a string that is implemented in Redback. Or if you didn't even like that and you had your own Python function, you would just pass the Python function in and it'll fit using that. At the same time, if you, for example, didn't like the sampler, so in Redback, there's about 15 samplers that are just directly implemented. So, or what that means is that you can just choose sampler equals, for example, ultranest or MC or dynasty, and you just specify the string and then it'll fit using that sampler. And what that enables is that there's a lot of benefits to cross-sampler validation. So being able to see whether you're getting the same posteriors for different samplers. But also different samplers are better suited to different things. So a nested sampler is far better at dealing with multimodal posteriors than, for example, MC is. Or, you might, in the future, you'll be able to use samplers that are using jacks. And so these will be a lot faster than anything available in pure Python or C. Because they can leverage GPUs, for example. And so again, if you don't like the sampler, you choose a different one that is available simply via string. Or if you're an even advanced user and you can write your own, or you have your own, you would just expose the likelihood and then again use the sampler as is. So the whole point is that this is how the whole modular interface works. The novice user, the choices are made. So the things like the prior are the default prior, but again, if you are an advanced user, you can expose these things to change the prior, change the likelihood, change the model, and various other things and so on. And again, in that last sort of line of code, I'm showing what the result looks like, which is again, just one line of code to show the plot at the bottom, which is just the fitted result. So the data is in, the markers are showing the data, and I've drawn 50 random models from the posterior and just plotted what the fit looks like. So same thing again, but just to showcase what things would look like differently if you, for example, wanted to fit flux data from Swift for a particular GRB. So again, I'm interested in fitting this model called the evolving magnetar. I want to use the Nestle sampler this time, and I want to get the data. So now I would get the data, and I'm interested in the flux data mode, and I'd do that. And within sort of a few seconds, it'll download the data from the Swift website and processes it, etc. But in this particular case, I'm also interested in fitting the luminosity data. So there's one line of code which is shown in terms of additional processing, which will turn this data, once you've loaded it up, into luminosity data, looking up things like the redshift, if it exists, or photon index from the website, from the Swift API. And so again, essentially everything is identical. Downloading the data. I'm using the default prior. This particular case, I want to use the Nestle sampler, so I just change the string. And now all of a sudden I have a result after fitting the model. And this is a pretty quick thing, so it'll take a few minutes at most. And in this particular case, I have, automatically generated this plot at the bottom, which is because it's afterglow data, and because I specified that it was in luminosity after doing the processing, it's just turned the various labels and things all on its own into showing what a luminosity versus time since burst looks like. And so again, the data is in black and the max likelihood estimate is shown in purple, and then 100 random draws from the posterior shown in red. Similar sort of thing, but you can also actually fit spectrums. So again, if you had some private data or some downloaded data for what the spectrum looks like, you would load that up into a spectrum class. In this particular case, I'm showing you how to actually expose the likelihood behavior itself. So I'm setting Redback likelihood, stock Gaussian likelihood. Yeah, I didn't have to do that. I could have just left it as the default, but this is just to show how you expose this behavior. And again, I'm fitting some sort of specific model, but if I didn't like it, I could fit my own. And now, I have the result object at the end, which is showing you, everything sort of collected in this object, and I can do result.plot spectrum. And I'm this time passing in some keyword arguments just to, change the aesthetics and show you how that works. And then all of a sudden I have a fitted spectrum. So again, the purple is the max likelihood and the red is the actual data, and the spectrum with the continuum emission from a blackbody and an absorption and emission line is shown as a fit. So how am I doing for time? I'm 33 minutes in. So, just also to highlight some more use cases, one of the things we've been really doing is, we've already been using this tool quite a bit in the last couple of years. So Redback was version 1 was sort of published in the sort of early July in 2023, and since then we've been updating and so on. And so, one of the things we've done is, for example, look at tidal disruption events. And so we fit a whole sample with a new model for tidal disruption events and see what that looks like. And so an example is sort of shown, in this plot at the top. And so the highlight here is that with Redback, one of the things that we're continuously doing is writing down better models for electromagnetic transient phenomena. And these models are just, again, seamlessly integrated. So an end user's knowledge of how the model works or how to actually get it to run is not something that stops them from using the model. The interface is always the same as it is for any other transient model. So, on the bottom is, this sort of new model for magnetar-driven superluminous supernovae that we've written down. And that was something we did with Connor Armand. And essentially, again, it's the same sort of thing where we've written up the model, and then it just becomes a callable function in Redback, and we can investigate what that looks like. But the whole point is that, we've been using this thing for a little while now to sort of do things like jointly analyze different types of electromagnetic transient data. So, for the classic case is the spectrum of photometry or gravitational wave and electromagnetic data, or kilonova, supernova that is accompanied by a GRB afterglow. And because this thing is a Bayesian inference framework, you get a lot of benefits that are, captured by the Bayesian inference sort of methodology. So in particular, instead of getting one max likelihood estimate of the parameters that describe your transient, you get actually a full posterior. And the benefits of a full posterior are something that I can go into a whole different talk. There's a lot of benefits. But you get things like hierarchical modeling. So if you're interested in understanding things like what are the population properties of your different transients, you can do that. If you want to do model selection, you can do that. Importance sampling and various other things. There's all these benefits that a Bayesian inference framework offers you that we get for essentially free. And so on the right-hand side, this is something that was led out of my students. So I'm really proud of her, showing you how to basically do joint afterglow and kilonovae and these systematics that you have to deal with if you take alternate approaches to fitting this data, essentially. And so this was a paper that we recently used it. And again, all of these models are just implicitly available in Redback. You don't have to do anything. It's just you pip install Redback, and you can do the exact same analysis without, doing anything else. Similarly, you can jointly fit, as I mentioned, the spectrum and photometry. And one of the highlights we had there was essentially you can use the spectrum to break degeneracies in your parameter estimation. So one of the big degeneracies in kilonova inference, or similarly with supernova inference, is the degeneracy between the opacity and the ejecta mass, for example. But now all of a sudden, if you have a spectrum alongside it and you fit both of them simultaneously, you can use the fact that the spectrum has to be the same. The spectrum is what ultimately generates the photometry. And you can use that to break the degeneracy, and you end up with much more precise estimates for your ejecta mass, and you don't have to marginalize over opacity, and you don't have to worry about things like when do specific emission lines emerge or disappear, and how do they affect the photometry, because you can put that into your spectral model. So a little bit about sort of the development and various things like that. So, it's built on modern software development practices. What that means is that one of the big things that we're very keen to sort of set up is continuous integration. So what that means is that for 81% of Redback, so Redback is about 13,000 lines of code now, is tested automatically on multiple different installations of Python for different Windows versions or Mac or whatever, automatically on every commit. That means that Redback almost always never breaks because of things like, oh, I can't install Redback. It breaks because of things like, oh, the physics is wrong. And that's, ideal because, we're not really software developers. We're physicists, and we want to rather, we don't want to go chasing up things like, oh, why does this not install on this Python version? We'd much rather worry about the astrophysics of the problem. And so originally this number was higher, but as time goes on and you add more and more models and things like that, it becomes harder and harder to maintain this high number. But 81% is incredibly high for the standards set by the field of astronomy and physics. The way this is maintained is also we request sort of a pull request system. So if you want to make changes to Redback, I'll show the GitHub repository in a sec, but essentially you have to fork it and you have to make a pull request, and then I or some other developer of Redback is going to look through it and approve it and merge it in. There's also a large library of examples and extensive docs. So the documentation is shown as a snippet on the right, for example, for the models of the physics you can change, for example. But there's also extensive documentation for the API. And one of the things that took us a long time to set up, but I'm really proud we did it, was that for every model that is implemented in Redback, there's a reference pointing to, at least one reference pointing to what paper you should look at if you're interested in how that model works. And for some models, there's quite a few. Sadly, for some models, the paper is just the Redback paper. That's because there's no other paper pointing out to it. And there's quite a lot of examples in the main GitHub repository as well. So hopefully to get anyone who's interested in using it set up and various other things. So a little bit more of the development. So as I mentioned, the paper that marked sort of the main public release of Redback was published in early 2024. But since then, we've been making continuous improvements to the package. So as I mentioned, one of the things that I and some of the core developers are particularly interested in are the models. So we're continuously improving the models. But it's also other things like, we're trying to get better integration with brokers and TNS so that we can ingest data more seamlessly and more data more seamlessly. We're also trying to set up things like an API for Fermi data and various other things. Similarly, one of the other developments that is pretty, hopefully coming out soon is that we're going to enable a backend with JAX for some specific models and some specific, a specific sampler. And what that'll enable is we'll get a massive speed up, and the code will become sort of GPU, CPU agnostic, at least for a few things. There's occasional dev user calls for tutorials, Q&As, and things like that. There's some tutorials that are hosted on YouTube if people are interested in sort of seeking those out. There's a Slack channel as well. And I would love to have, more users, more developers. And so if there's particular things that you're interested in doing, you think this tool could do, I'd love to hear about it. So that is Redback. I've got this conclusion slide, but because there's, I think, a few people that might be interested in a few things, I'll go through a couple of other slides just quickly, which are in the extra slides section. But if you scan this barcode, you'll be taken to the GitHub page. Of course, you can just Google it, and I'm sure you'll find it. And so in summary, Redback is sort of an open source, pip installable Python package for modeling and inference of electromagnetic transient data. Over 100 models and 15 samplers are sort of directly implemented. And what that means is you can swap models and samplers by simply changing a string. In particular, if you're interested in doing GRB afterglows, TDEs, kilonovae, supernovae, F-bots, millisecond magnetars, and various other things, there's plenty of models that are only available in Redback that many would consider state-of-the-art and that are only available there. There's an interface to download and process data or simulate your data as well for realistic surveys. There's a large library of examples, extensive docs. And yeah, as I mentioned, I'm happy to chat for anyone who's interested in talking about things further. So, as I said, I have a couple of extra slides, but because it's 45 minutes, I can go through them. But I thought, because there's people here that would probably be pretty familiar with SNANA and MOSFET, I can just explicitly go through sort of the comparisons you can draw between those two tools. So Priscilla, it's up to you now, whether you want me to go through those two slides or I can take that.
Yes, please go ahead.
Awesome. So, in particular, so for example, a tool that is quite common in the field for a long time for inference of transients is this tool called MOSFET. And so the main sort of comparison I want and contrast to MOSFET, and this is something that I'm saying as far as I know. So, I'm not a developer of MOSFET. I'm just, someone who tried to use it for a long time, a little while ago. And so, Redback has a much larger library of models. And so there's a one-line interface to using your own model, which is particularly key. So if you are someone who develops models, it's quite a lot easier to put your model into Redback than it is into MOSFET. The models range in complexity. So as far as I know, there are no numerical simulation surrogates in MOSFET. So that is something that you can only do with Redback in comparison. And then there's transients that are just simply not available as something that you can fit in MOSFET, such as GRB afterglows and various other things. And as well as things like you can jointly fit, gravitational waves, GRBs, and spectrum photometry. You can do realistic survey simulations. You can fit any type of data, be it magnitudes, luminosity, flux, and flux density, Poisson data, or spectra, or a Gaussian process plus mean model. All of these things are flexible. Redback is also much faster, so this is something that we've been able to benchmark with a few people who are proficient users of MOSFET. And the same sampler, the same data, if you fit with Redback, so in particular SN 2018 IBP, it takes 8 minutes to fit with Redback. It takes about a day to fit with MOSFET. So the difference is just coming from how fast the models written in Redback are as opposed to MOSFET. And again, as I mentioned, it's just integrated with way more samplers. So this is particularly important because that 8 minutes was with the same sampler. But now if you also leverage the fact that there's newer generations of samplers, you get much more speed up and much better functionality. to use machine learning and things like that to generate samples more efficiently. And so then a difference with SNANA, which I know a lot of people in desk like to use, is what I would say is that it's sort of a very different end goal. The main primary sort of models in Redback are physically interpretable models where an inference with those models is the primary goal for single or small samples of transients. And if you're really interested, you also would look at population properties, source parameters. So not ever something about the host or cosmology. This is subjective, but at least many people who have used SNANA and Redback tell me that it's far easier to add models in Redback and simulate different outputs. And especially if it's a sort of a physical thing, so if I want to see what an F-bot or a TDE looks like in Rubin's ETF, ultrasat, or whatever, if I just change the black hole mass in a particular model, that's far easier to do in Redback and generate lots of data. Simulations in Redback are realistic enough for astrophysics, but they're definitely not realistic enough for cosmology. So if you are interested in doing cosmological simulations, ultimately to simulate, 10 years of 1As so that you can see what Hubble constant or whatever else will be, Redback is not the tool for you unless you also make the effort of putting your own simulation module in. Essentially because we make sacrifices to the simulator that are, not basically we sacrifice precision in to get some speed. And so the precision basically means that you can't do precise estimates for cosmological purposes. But if you're interested in astrophysics where our uncertainties are far larger, the precision doesn't matter for the precision we are sacrificing in the simulator. And then, as I mentioned before, Redback will, for some models, will become GPU, CPU agnostic. And so, you will be able to, for example, go for an RNet model, full posteriors in seconds, just enabled by, Jack's backend and Jack's model. And yeah, so I'll conclude there, and yeah, I'll take any questions. So thanks so much.
Thank you so much, Nikhil, for presenting this powerful tool. It's great to know there is this versatile way to connect observations, statistics, and physics for many different types of transients. So thank you for presenting today.
Thanks, Priscilla. Thanks for having me.